Now we will discuss about the signal and communication system, subject of principle of communication. So what is the communication system? Communication system designed to transmit and receive information. The block diagram of communication system is given here. A message signal is generated from the source signal and transmitted through the with the help of transmitter, and then this signal is transmitted on a channel, and there are some noise also mixing here in channel, and then this signal is received at the by the receiver, and after receiving, the receiver convert its signal message signal into the original source signal, and this signal received at the output of the receivers. So a discrete time signal is defined at discrete times. So this is the representation of discrete time signal in the form of digitals. So signal is xn equal to a into an, where n is the 0, 1, 2, 3, and so on. So this is the discrete time signal is defined at discrete times. And what is the elementary signals? Sinusoidal and exponential signals. Sinusoidal and exponential are important in signal and systems analysis because they arise naturally in the solution of differential equations. Sinusoidal signal can express in either of two ways. Cyclic frequency for equal to a sine 2 pi f naught t, or equal to a sine 2 pi upon t naught into t. Radian frequency for a sine omega naught t, where omega naught equal to 1 upon omega naught equal to 2 pi f naught or 2 pi upon t naught, where t naught time period of the sinusoidal wave. So sinusoidal and exponential signals xt equal to a sine 2 pi f naught t plus theta, and also a sine omega naught t plus theta. This is the sinusoidal signals, and xt equal to a into e to the power j omega t, or equal to a into cos omega naught t plus j sin omega naught t, where theta is the phase of sinusoidal wave and a amplitude of a sinusoidal or exponential signals, where f naught is a fundamental cyclic frequency of sinusoidal signal. Omega naught is the radian frequency here. So what is the unit step function? So unit step function ut equal to 1 if t is greater than 0, and equal to 1 upon t if t equal to 0, and ut equal to 0 if t is less than 0. So there is two graphs. First is precise graph and second common U graph between unit step function and time period. Next one is the signum function is closely related to the unit step function. If signum function equal to 1 if t is greater than 0, and equal to 0 when t equal to 0, and have the minus 1 value if t is less than 0. So signum function also equal to 2ut minus 1. So in these two graphs, the first is precise graph and second is the commonly used graph for the signum function versus time. Next, unit ramp function. So in unit ramp function is the integral of the unit step function. It is called the unit ramp function because for positive t, its slope is 1 amplitude unit per time, and ramp t equal to t if t is greater than 0 and equal to 0 if t is less than or equal to 0. And also unit ramp function we can explain or we can write that equal to minus infinity to t u lambda d lambda equal to t u t. So this is the unit ramp function. Next one is the what is the rectangular pulse of gate functions. So rectangular pulse delta at equal to 1 upon a when t modulus of t is less than a upon 2 and delta at equal to 0 if modulus of t is greater than a by 2. So the shape of rectangular pulse or gate function we can see in this waveform diagram between draw delta alpha t versus time period. So as alpha approach 0, gt approach a unit step and gt approach a unit impulse. So in this graphical representation, function that approach unit step and unit impulse. So unit impulse function is the derivative of the unit step function, or unit step is the integral of the unit impulse functions. Representation of impulse function. The area under an impulse is called its strength or weight. It is represented graphically by a vertical arrow. An impulse with a strength of 1 is called a unit impulse. So in first representation of a unit impulse and second is the shifted impulse of amplitude by 5. So that is the representation of impulse functions. What is the property of the impulse functions? So first is the sampling property. In sampling property, we integrate the gt delta t minus t naught dt from infinite to infinite with respect to time, and this will be equal to g t naught, and the sampling property delta into a t minus t naught equal to 1 upon a modulus of a delta t minus t0, and the replication property is gt into delta t equal to gt. So this is the property of the impulse function. Next is the unit impulse train. The unit impulse train is a sum of infinite uniformly spaced impulse and age given by delta t equal to summation of minus infinite to infinite delta t minus n t, where n integer, and this is the unit impulse train, which is as shown in this graphical diagrams, that is draw between delta t versus time. The unit rectangle function. So what is the unit rectangle function? The unit rectangle or gate signal can be represented as combination of two shifted units step signal are shown. Rectangular t equal to u t plus a minus u t minus a. So this is the unit rectangle function representation by this graph between rectangular function versus time. A rectangular pulse whose height and area are both one, what its base width is not, is called unit triangle function. The unit triangle is related to the unit rectangle through an operation called convolution. So this is the unit triangle function. In sync function, the sync function equal to sine pi t upon pi t, and that is represented by in this graphical representation between sync function versus time t and the variation of sync function with the time, as we can see in this graphs. Discrete time signals. Sampling is the acquisition of the value of a continuous time signal at discrete point in time. So xt is continuous time signal. Xn is a discrete time signal. So xn equal to x into n ts, where ts is the time between different samples. Discrete time exponential and sinusoidal signals. DT signals can be defined in a manner analogous to their continuous time counterparts. So xn equal to a sine 2 pi n upon n naught plus theta, and also a sine 2 pi f naught n plus theta. This is the discrete time sinusoidal signal. And xn equal to alpha power to n. So discrete time exponential signal. This is the where n is the discrete time and a is the amplitude. Theta is the phase shifting radians, and naught is the discrete period of the wave. And also 1 upon n naught equal to f naught equal to omega ohm divided by 2 pi equal to discrete frequency. F naught is the discrete frequency. There are different discrete time sinusoidal signals, and there are different time period of the different discrete time sinusoidal signal, which we can represent it in different diagrams of graphical presentation. Discrete time unit step function or unit sequence function. So un equal to 1 when n greater than 0, otherwise will be 0 when n less than 0. So discrete time unit step function or unit sequence can be represented by this graphical representation between un versus n. Discrete time unit ramp function. Ramp function, unit ramp function, ramp n equal to n when n greater than or equal to 0 and otherwise 0 when n less than 0 or equal to n summation of minus infinity to n u m minus 1. So this is the discrete time unit ramp function, and graphical representation also represented in this graph by the different value of different amplitude value of impulse. Discrete time unit impulse function or unit pulse sequence. So delta n equal to 1 when n equal to 0, otherwise delta n equal to 0 when n not equal to 0. So delta n equal to delta an for any non-zero finite integer. This is the discrete time unit impulse function or unit pulse sequence. The discrete time unit impulse is a function in the ordinary sense in contrast with the continuous time unit impulse, and it has a sampling property, and also it has no scaling property. For example, delta n equal to delta an for any non-zero finite integer a. So what is the operation of signals? Sometime a given mathematical function may completely describe a signal. Different operations are required for different purpose of arbitrary signals. The operation on signals can be time shifting, time scaling, and time inversion or time holding. So the operation of signals can be time shifting, time scaling, and time inversion or time holding. So first is the time shifting. The original signal xt is shifted by the n amount of t naught in this time shifting, and xt and x t minus t naught signal delay and shift to the right in this second diagram. First diagram show the xt signal and second diagram show the xt minus t naught, that is the shift to the right. In this diagram, the xt and xt naught plus signal advance shift to the left in this diagram. So here is signal is shifted to the left for xt plus t naught. Next is the time scaling. In time scaling for the given function xt and xat is the time scale version of the xt. For a greater than 1, period of function xt reduce and function speed up, graph of the function shrinks. For if a less than 1, the period of the xt increase and the function slow down, graph of the function expands. For a given example, here xt and v are to find yt equal to x2t. So first diagram represents a period of xt, and second one is the for the yt equal to x into 2t. So this is the time scaling function. For one is xt and second is yt equal to x into 2t. That is represented in this graph. Time scaling function given yt, find wt equal to y3t and vt also y into t by 3. So there are given function yt, and second is the wt equal to y into 3t, that is represented in second diagram. And also next function vt equal to y into t by 3, that is also represented or draw in graph third or diagram third. Next one is the time reversal. In time reversal is also called time folding. In time reversal, signal is reversed with respect to time, or yt equal to x minus t is obtained for the given function. And here is the representation of time reversal signals. First, for the representation for the xt versus t, and second for the yt equal to x minus t. So this is the time reversal signal representation in these two diagrams. Operation of discrete time functions. So time shifting n tends to n plus n naught. N naught is an integer. So here first diagram represents the gn, and second one represents the gn plus 3. So here is the operation of discrete time function, where we have the value of n, different value of n and n plus 3, and also gn plus 3. Operation of discrete function in scaling signal compression. So n tends to kn, k an integer that is greater than 1. So here, if we take the value of n, 0, 1, 2, 3, 4, so what is the value of 2n? It will be 0, 2, 4, 6, 8. And what is the value of g2n? This will also equal to 2, 4, 6, 8, and 10. So this is the scaling signal compression. Next, classification of signals. So in classification of signal, here is deterministic and non-deterministic signals, periodic and aperiodic signals, periodic, even and odd signals, also energy and power signals. So there are the different signals here. Deterministic and non-deterministic signals. Deterministic signals behavior of these signals is predictable with respect to time. There is no uncertainty with respect to its value at any time. These signals can be expressed mathematically. For example, xt equal to sine 3t is deterministic signals. And also in this diagram, non-deterministic or random signals. So in this random signals, behavior of these signal is random, not predictable with respect to time. So there is an uncertainty with respect to its value at any time. These signals can't be expressed mathematically. For example, thermal noise generated a non-deterministic signal. You can see in this diagram of waveforms. Periodic and non-periodic signals. Given xt is a continuous time signals and xt is a periodic, if xt equal to x t plus t naught for any t and any integer n, for example xt equal to a cos omega t. So x into t plus t naught equal to a cos omega t plus t naught or equal to a cos omega t plus omega t naught, and also this will be equal to a cos omega t plus 2 pi. Note t naught equal to 1 upon f naught here and omega equal to 2 pi f naught. This is the example of periodic and signals. For non-periodic signals, if xt is not equal to x t plus t naught, a non-periodic signal is assumed to have a periodic t equal to infinite. So example of non-periodic signal is an exponential signals. Important condition for periodicity of discrete time signals. A discrete time signal is periodic if xn equal to xn plus n. For satisfying the above condition, the frequency of the discrete time signal should be ratio of two integer or f naught equal to k upon n. So xt equal to x1t plus x2t and xt plus t equal to x1t plus m1t1 plus x2 into t plus m2 t2, where m1 t1 equal to m2 t2 equal to t naught, fundamental period of the signal. For example, cos t pi by 3 plus sin t pi by 4. So t1 equal to 2 pi upon pi by 3 equal to 6 and t2 equal to here 2 pi divided by pi by 4 then equal to 8 and t1 upon t2 equal to 6 upon 8 or 3 by 4. This is the rational number equal to m2 upon m1, where m1 t1 equal to m2 t2, and find the m1 and m2. So here 6.4 equal to 3.8 equal to 24 equal to t naught, that is the fundamental period. So xt, sum of periodic signals may not always be periodic. So xt equal to x1t plus x2t equal to cos t plus sine under root 2t, where t1 is 2 pi or 2 pi, t2 is the 2 pi upon square root of 2. So t1 upon t2 is equal to square root upon 2. Note t1 upon t2 equal to square root 2 is an irrational number. So xt is a aperiodic signal. Next, even and odd signals. So even function gt equal to g minus t and odd function gt equal to minus gt. So here is the even or signals representation in different waveforms. That is graph between signals versus time. Signal may be even function or odd functions here. So even and odd parts of function, the even parts of a function is GE t equal to gt plus g minus t divided by 2, and the odd part of the function g naught t equal to gt minus g minus t divided by 2. So this is the even part and odd part of the function. A function whose even part is 0 is odd, and a function whose odd part is 0 is even. So these are the even and odd parts of the function. Here, various combination of even and odd functions. So there are different function type, both even, both odd, and even and odd, and sum, difference, product, and quotient. So function type is the both even. In that case, sum will be even, and difference will be also even, and product also even, and quotient will be even. Next, if both functions are odd, in that case, the sum will be odd, difference will be also odd, but the product will be even, and quotient will be even. And if the function type is even and odd, both even and odd, in that case, sum neither, difference will be neither, and product is odd, and quotient will be also odd. So there are various combinations of even and odd functions in different cases. Product of even and odd functions. So product of two even function is in this diagram. So here one function is g1t and second function is the g2t, and these are product, and after product the output as the second diagram, that is the waveforms. So the product of g1t into g2t versus time period. So this is the result of the product of even and odd functions that is given in second waveform diagram. Next, product of an even function and an odd function. So here is also g1t function and g2t function. Here g1 function is purely sinusoidal and g2 is the square pulse or square function or pulse train. So product of these two even function and odd function will be equal to g1t and g2t, which is draw in second form of waveform, and product of even function and odd function. In that case, if the g1 function is the sinusoidal and g2 function is also cosine function, so the product of the sine and cosine even or odd function is equal to, in that second waveform diagram, the waveform will be resultant waveform in second waveform diagram, in which the waveform between G1T and G2T, product of G1T and G2T purchase time period. So this is the product of two sine and cosine waveforms. And next, if we multiply two waves, one is the sinusoidal and second is the triangular. So after the product, the resultant waveform will be as form of a second diagram waveform, which is the product of G1 and G2, even and odd functions. So this is the resultant waveform in this second diagram, in which two even or odd waveform, one is sinusoidal and second is triangular. So these are the some reference books for this topics. So first book is signal processing by the focus, and second digital communication by the signal. There are some multi-choice questions here also. So that is very important and very interesting to clear the concept of this topics. So question first, a system is said to be shift invariant only if option A shift in the input signal also result in the corresponding shift in the output. Option B, a shift in the input signal does not exhibit the corresponding shift in the output. Option C, a shifting level does not vary in input as well as output. And option D, a shifting at input does not affect the output. So correct answer here, option A system is said to be shift invariant if a shift in the input signal also result in the corresponding shift in the output. So here correct answer is option A. Next, which condition determines the causality of the LTI system in terms of its impulse response? So option A, only if the value of an impulse response is 0 for all negative values of time. Option B, only if the value of an impulse response is unity for all negative impulse of time. C option, only if the value of the impulse response if infinity for all negative values of time. And option D, only if the value of an impulse response is negative for all negative values of time. So here correct answer for the condition determined by the causality of the LTI system is the option A. Correct here answer. Next questions, under which condition does an initially relaxed system become unstable? Option A, only if bounded input generates unbounded output. Option B, only if bounded input generates bounded output. Option C, only if unbounded input generates unbounded output. And option D, only if unbounded input generates bounded output. So here correct answer is option A. Under which condition does the initially relaxed system become unstable? When only if bounded input generate unbounded output. So correct answer here is option A. An equalizer used to compensate the distortion in the communication system by faithful recovery of an original signal in nothing. What is illustration of option A, static system, option B, dynamic system, option C, invertible systems, option D, none of the above. So correct answer is option C, invertible systems. In next, which block of the discrete time system require memory in order to store the previous inputs? Option A, adder, option B, signal multiplier, option D, unit delay, and option D is the unit advance. So here the discrete time system require memory in order to store the previous inputs. So here correct answer is the unit delay. So correct option is option C in this question. Next question, which among the following belongs to the category of non-recursive system? Non-recursive system. Option A casual FIR system. Option B, non-casual FIR system. Option C, casual double IR system. Option D, non-casual IIR system. So for the category of non-recursive systems, here the correct answer is the casual FIR system. So correct option here is the casual FIR system, which is the option A. Next question. A system is said to be shift invariant only if a system is the input signal also result in the corresponding shift in the output. Option B, a shift in the input signal does not exhibit the corresponding shift in the output. Option C, a shifting level does not vary in the inputs as well as output. Option D, a shifting at input does not affect the output. So here correct answer is the option A, where a system is said to be shift invariantly only if a shift in the input signal also result in the corresponding shift in the output. So this is the correct answer, option A here. In next, which condition determine the causality of the LTI system in terms of its impulse? So option A, only if the value of an impulse response is 0 for all negative values of time. Option B, only if the value of an impulse response is unity for all negative values of time. Option C, only if the value of an impulse response is infinity for all negative values of time. Option D, only if the value of an impulse response is negative for all negative value of time. So here correct answer is the option A. That is the only if the value of an impulse response is 0 for all negative value of time. And last question, why is the impulse duration important? Why is the impulse duration duration or time important because it is 0 in option A. It is changed with time. Option B. In option C, it approach 0. And option D, it is depend on the situation. So here correct option is C, its approach to 0. So the impulse duration important because it approach to 0. So thank you very much.